Today's theme is random variation and increase of information. Some improvised experts contend that it is impossible that a random variation can ever increase the content of information of an already highly efficient organism or computer program. These people tend to make very general statements, maybe because they feel that the more general the statement, the more the opponent might have a hard time to dispute it. I'll show once again that it is the very generality of their claims that makes it much easier to debunk them. One only needs a simple, well-constructed example to show why they're incorrect. What I'm going to discuss is a toy model. It does not necessarily reflect literally how complex biological machines manage to survive in their surrounding. This is also a straightforward example of a computer program that has evolved initially to do an excellent job to perform a difficult task. Then we'll see what can happen after one key single mutation affects a program. Can it become even better at doing this job? This is, in the end, what the people I'm talking about claim is impossible. They say that a well-constructed, highly efficient, task-oriented program would always become less efficient to perform tasks if a random mutation occurs to disrupt the original script. So these people contend that the information content always decreases as a consequence of any random mutation. Other people counter rightly that in a very few cases a random mutation can make it possible to adapt to do one new task or just a better job. Here's how our example works. That's our ugly living organism. What you should really concentrate your attention on is the computer program and its information content, but I've also designed this presentation to help make some parallels with the true living world using analogies. So our little ugly swimming monster is surrounded by 8 distinct representative elements, eventually a subset of a much larger and richer pool. Think of proteins, food, whatever. For us, they are figures of different shapes, each identified uniquely by a prime number in progressive order. In this biological metaphor, we can imagine that the shapes are part of a much larger environment. Survival in such environment is dictated by the ability to solve these and many other unstated problems. We posit that all these algorithmic machines or living organisms have managed to adapt generation after generation to do many tasks, or have been built to do so. To be able to recognize some of the numbered shapes that are in the pool would give some advantage to the members of the population that have some system to recognize what element they have come across to. The example works fine if you think of that some shapes are food supplies, hazardous elements. In any case, we assume that to identify the object might gain the machine a benefit. Our swimming box also has 2 terminals which are in contact with the external environment, then attached to algorithmic unit inside the cell. The terminals can attach momentarily and then release 2 distinct shapes at the same time every time. The inside triangular unit can process these 2 inputs from the 2 terminals and produce an integrated output for any pair. The aim of the game is to identify or guess which are those 2 units. The average unevolved cell will have developed no good guessing mechanism. Either no program is running at all to produce an output from the 2 input sources, or it expresses a random guess. The cell hasn't developed any mechanism, that is, any program, to take advantage of this particular environment. Any organism that can make a better guess than random will have an advantage over the others. With a random guess, we can calculate the probability to guess the pair right, which is 1 part in 28, and which is the number of distinct pairs in the pool. The common cell has therefore each time around 3.6% chances to identify the pair. This is the reference organism, the reference program against which we have to measure all others. Any organism that can do better than 3.6% must have stored more information, it must be more complex, and we would be at an advantage in this environment. And there it comes, the alien germ, the amazing computer program that will outperform all others. It is a machine that has an amazing property. It has an increased efficiency by a factor of 20 over a random guess. It has 71% chances to identify exactly the pair of prime numbers. How does she do that? Well, this is the program with high information content. You can also assume I myself designed it, like a watch on the beach, or it has evolved. This real monster can in fact perform an amazing task. It can sum the numbers that we associated with the shapes. It then reads the output and makes a guess on the two numbers that produced that outcome. It's a schematic way of how you could do that. You imagine that it contains an algorithm, and it also exploits a sister copy of the device inside the body, together with a set of shapes identical to those in the environment. It then passes all of them through the algorithm and checks whenever the output coincides with that produced by the device that is in contact with the environment. To summarize, the algorithm sums the two numbers, and the outcome, the result of the algorithm, is read. The overall probability to make an exact guess is 5 parts in 7, 71%. That's the overall count. Whether the guess is correct depends on the specific pair and on the output. For example, if the cell reads the number 10, there is a 100% chance to identify the inputs, because only the sum of the primes 3 plus 7 can give 10. At the other extreme, the number 18 can be obtained as the sum of 1 and 17, 5 and 13, 7 and 11. In this case, only 1 in 3 times the organism makes the correct guess by reading the output. As we see, there is an astonishing increase in performance by a factor of 20 on average over the machine that had no algorithm. This would represent a big advantage in order to survive and reproduce. One would guess that to associate a prime number to the inputs and in the algorithm is not a trivial feature. We don't care at this point because we have assumed that it is either the product of evolution or the product of an intelligent programmer. This machine is highly efficient, task-oriented, complex, with very high information content and very able to survive. Just to list primes is a non-trivial task, so we should all agree that this program is almost a miracle. The question now becomes, what happens if a random mutation occurs? Some people would say that the information content of this precious gem of engineering can only decrease. Let's see. Suppose some of these wonderful machines will experience random mutations. Many would be indeed deleterious. For example, the capacity to list the primes might be lost. They might modify any key part of the program and make it non-functional. But the central question is, can one random mutation in principle increase the information content of this highly efficient and very well adapted program? Yes, there is one key mutation, a single-step mutation, that would make the process a stunning 100% efficient. That is, for every output, the machine will correctly identify each and every time the pair that produced that outcome. How is that possible? Simple, the summation rule is turned into a multiplication rule. In terms of computer programming, that's a change in one only symbol in the whole program, a mutation that could arise by chance given enough attempts. A plus turns into a times. I'll leave it to you as an exercise to verify that if the algorithm multiplies the numbers, there is no way the program can ever make a wrong guess. For example, here are the 3 numbers that in the parent machine produced the same outcome and could not be distinguished with absolute certainty. Now instead we get 17, 65 and 77. One could imagine other mutations, that's not all. For example, the sum could have become a subtraction. Overall, this is a 50% chance guessing machine, still much better than random guessing, but on average, worse than the summing machine. One could say that this particular random mutation has decreased the overall information content. However, that doesn't mean that the machine that subtracts primes is doomed. It might depend on the environment. Let's suppose not all shapes are equally important for survival. For example, to identify 1 and 17 rather than any other pair might give a crucial advantage to the machine or organism that could do that most efficiently. In this case, the subtracting machine is much better than the summing machine because it would always have 100% chances to identify the pair 1 and 17 correctly, to be compared to 33%. Concluding, a random mutation can, albeit rarely, increase the information content of an already very sophisticated program. This is because, for how evolved the program is, we cannot assume it has evolved to the maximum content of information allowed. We investigated one class of short programs, a closed set. In the open set of all programs, one cannot claim to have achieved the point of maximum information content just because it says so. We have also seen that even if the overall information content decreases with a mutation, that could still give some advantage in performing one task which is crucial for survival.